Okay, in this video, we're going to be jumping into section 9.2. And again, this is going to be very similar to what we did in the last section. All these sections are very highly related. In the last section, 9.1, we looked at the inferences about two percentages. We looked at like what percentage of males and females completed their associate's degrees, what percentage of truck drivers versus car drivers like wore their seatbelt. So in this section, we're going to be dealing again with the same concept of comparing two things, but we're going to be comparing two averages. In the formula sheet, you'll be able to see that we're going to be in this bottom right box. So if the bottom left box was 9.1, over here is 9.2. And kind of awkwardly, 9.3 is the box that's actually up above. So we're going to see again, there's a nice connection between these first two sections, and 9.3 is kind of the oddball out. It's not too bad, and we'll see that in the next section. But when we compare both sides, we'll see here again that there's going to be a hypothesis test and a confidence interval that we can attempt to use. We can see the calculator commands and all the stuff that we need in order to find in the problem in order for the calculator to be able to crunch some stuff out. We'll see that in the last section again, remember that our goal was to try to ultimately find what a P1 minus a P2 was. That was a part of the green hypotheses that we created. And so today we have something very similar. We're interested in an average 1 minus an average 2, a mu1 minus mu2. So if I take a look back at the notes, we'll run down and do a quick overview of kind of what this test looks like. We'll see here that, again, we have each of our black sets of hypotheses, which are pretty standard, just comparing two averages in the same ways we always do. And then we have these new green hypotheses that we've been talking about. But you might notice that these green hypotheses have something a little bit different in them. They have this new awkward letter, and it's going to be this value that occurs down here in the test statistic, value of delta. So this right here is a Greek letter delta. It's got a little subscript of a 0 because it's the number that appears in the hypotheses. And most of the time, that value of delta is going to be a 0. Most of the time it's a 0. In fact, we'll see in our first example today, it's very clearly a 0. But it's just the number that kind of occurs in the green hypotheses. So again, don't worry about it too much. We'll see it as we kind of progress through the first example. We'll see then that what we're going to be doing is listing out our sample evidence. We're going to be computing all these different things here. We're going to be doing some checks to make sure that our X bars fall into a nice T distribution. And that would give me a distribution for X bar 1 minus X bar 2. The things that I have to check is that the population for each sample, or from where each sample is taken, is normal, or that each sample is a big enough size. I'll then go ahead and do a 2-sample t-test. We'll see how that works in a moment. Okay. We'll draw a picture, label everything as we always do, calculate our p-values, reach a conclusion. Okay. Now, since we're not in class together today, I think it'll be actually a little bit easier and more streamlined for me to skip example 1 and save that as one for you to actually go try to look at on your own. And we're going to start here in this video by taking a look at example 2. Example 2 is a thrilling question about snap bean storage. If you have no idea what a snap bean is, you can just Google it really quickly to see what it looks like. And if you don't care at all, then don't worry about it. All right, but let's take a look at what we have here and try to see how this is something that's a comparison of two averages. All right, so here's what we got. A new method of storing snap beans is believed to retain more ascorbic acid than the old method of storage. In an experiment, the snap beans were harvested under uniform conditions and frozen in 250 equally sized packages. 100 of those packages were randomly selected, and they were stored with the new method. The other 150 were stored with the old method. Subsequently, ascorbic acid determinations were made, and the following summary statistics were calculated. We want to go ahead and perform a test ultimately to see if this new method is actually better than the old method. This is going to be our objective here. Is the new method actually better than the old? So you can see here in the table, I kind of have some things written out about what happened in the new method and what happened in the old method. I have a sample mean amount, and I have a standard deviation. And so maybe I could go ahead and I could start to write out the following values. Okay. Mean number 1. This is before I write my hypotheses, but maybe mean number 1 stands for the average ascorbic acid retained by the new method, right? Like, I don't know what that average is going to be. I have a sample average of 450, but I don't know what the overall average is for like every single snap bean that I would actually possibly ever come across. I could also see that there's an average 2, which is maybe the average ascorbic acid retained by the old method. And again, once I have these symbols written down, it can become pretty darn easy to go ahead and start to see how I could shape up my hypotheses. I know that my first hypothesis is going to look like mean 1 is equal to mean 2, and that's kind of squaring off against, well, a different comparison between these two means. If I want to test to see if the new method is better, that would mean that average number 1 should be higher than average number 2. So these are my black hypotheses, but underneath them I can kind of squeeze in my associated green hypotheses. Notice that in the first one, if I subtract mean 2 to the other side, I should get 0 because the original means were equal. And if over here I do mean 1 minus mean 2, that's a big number minus a small number, that should get me something that is greater than 0. And so I'm trying to figure out which one of these is the more reasonable conclusion to hold. Okay, so I'll start by writing out my evidence. And this isn't too bad. Let's see what we got here. To go ahead and work with this idea of the evidence, I need to record what I have for each sample. So X bar 1, that'll be the average of the sample from the new method. So that's 450. I can see that S number 1 would be 20. And I would also need to know N number 1, which is how many bags did I actually store with this new method? Go back and look in the problem really quick to see if you can discover how many bags were actually stored according to the new method. You should be able to see that the answer is 100. If I did the same sort of value determinations for the second sample for this old method, I see that there are 150 packages that are put there. I'll also see that I calculate in X bar 1 minus in X bar 2. And of course, when I do this, I should be able to see that the total result is 40. The last value that I want to often think about here is my delta 0. Remember, that's the number that is occurring in the hypothesis. So I already kind of have it written right here. There's delta 0. Oh, and it looks like, no surprise, like we said before, most oftentimes it's 0. We'll see in a later example a time when it's not 0. Okay, the next thing I'm going to have to do is the checks. I want to check to see if my X bar 1 minus X bar 2, which is 40, is that rare? Is that not rare? You know, would I expect that to happen just by chance? So I want to go ahead and check the conditions. One of the conditions here, though, is remember that n could be greater than or equal to 30. But I technically have to check this for n1 and for n2. And of course, this is very clearly going to be met. So X bar 1 minus X bar 2 has a t-distribution. The last thing that I would need to figure out here is the value of t, like what is the actual t-score? How many jumps above or below what's expected is this X bar 1 minus X bar 2? The calculator will tackle that for us, and so we'll kind of tackle that collectively in the next step. So again, I draw a number line. There are a whole bunch of different X bar 1s minus X bar 2s that I could ever get, and they all fall into a nice t-distribution. We know that we're assuming that H0 is true. So when we ask, what did we expect to get when we did X bar 1 minus X bar 2? Well, we would have expected to get 0, because that's what happens when I actually subtract the averages. The weird part, though, is we didn't get 0. We got a much larger value of 40. And so we might want to know, is that value too large? So we can set up here a p-value. Our p-value is that blue space, and so it would be calculated when we get an X bar 1 minus an X bar 2 greater than a 40. The calculator will figure out what this number is for us once we do the test. The other thing that we can write here is a little t to indicate our t-scores. We know that 0 has a t-score of 0, and we're unsure of the t-score for 40 yet. But once the calculator tells us that, we can fill it in. So I'm going to go to my calculator here really quickly, and I'm going to get ready to run the test. So looking at the formula sheet, you should be able to tell what test I'm interested in running. Take a look back at the formula sheet to see if you can tell. It seems like the test that I should be running is this number 4, a 2-sample t-test. Notice that when I click it, I have an option again for data and stats. And I'm going to go with stats because this is the type of information that I have. I'm going to fill in the information based on the numbers that we were or have already written down in the problem. And then I'll write down my alternative hypothesis, which said that mean 1 was going to be bigger than mean 2. You'll see below that there's an option for pooled, no or yes. We're always going to leave that as no. Just don't ever switch it. Don't just pretend it's not even there. It has something else to do with assumptions about population variances, and it's just not stuff we're going to be getting into this semester. So we can just go right to calculate to see what we get. Now immediately I should be able to take a look at that t-score and then pick my jaw up off the ground because that t-score is humongous. 9.5 jumps above average. That 40 is so far above average right now. That's crazy. I can even then see that that's reflected in the p-value, which is 0.000. Let's see, I need 18 zeros. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, then a 1. Okay, you can of course just round that immediately to roughly 4 places, so roughly 0. This has like almost no chance of happening just by luck. So I can immediately say that, yeah, even if alpha here is given as 1%, this is absolutely super, super rare. So how well does H0 fit? H0 says, you just got this by chance. And we go, I don't know about that. That seems pretty strange. This is a good time to reject H0. So we'll go ahead and write our conclusion. It is extremely rare to get a difference of sample means of 40 by chance if the real difference is 0. That's again exactly what the p-value tells us. It's exactly what our picture is showing us. My second sentence then, therefore, we have enough evidence to believe whatever H1 says. But if I look at what H1 says, we have enough evidence to believe the new method is better on average than the old method. Seems like this new method is, I'm definitely going to put my money on that it's better. Okay, so again, hopefully this doesn't feel like too much of a deviation from anything else that we've been dealing with here. I'm going to ask you right now to go ahead and before you start the next video, which will take a look at part B of this question, go back and see if you can try to actually complete something like example 1. See if you understand the actual idea. Just be careful on example 1. You'll find that it is a two-tailed test, so make sure you make the appropriate adjustments there. All right, so go try that, and then I'll see you for part B in the next example.